Okay, so the torsor of lifts of the Frobenius. So I'm going to talk about torsors of lifts of the Frobenius. Of lifts of the Frobenius. Mod p squared. Okay, so here's the setup. So I'm just going to state, so A is going to be a commutative ring. B is going to be, let's say, an A algebra. And let's say they're both flat over ZP for simplicity. So in particular, multiplication by P is going to be injective. So let delta 1 and delta 2 be two from A to B and be two P derivations. Okay, one, the first comment I want to say is that this is ZP linear. This is a ZP linear map from A to B. So it's a map from A to B. Two, okay, so let's say D defined to be equal to the difference of these, mod P, is a derivation of the Frobenius. And it's well defined, so furthermore, it is well defined on the source modulo P squared. Okay, and so let me prove this. And let me see what a derivation of the Frobenius is here. Let me do this in a box here. Okay, so this is a map from A1 to B0. Okay, so I'm going to use this notation that A to the n is A mod P to the n plus 1, and the same for B. Okay, so here, this is a map like this, okay, and we're going to have a derivation is from here to here. This is going to be in characteristic P. Let's say A1 plus A2. It's just going to have this. So it's additive, and then it satisfies a Leibniz rule, but the Leibniz rule involves the characteristic P Frobenius. Okay, so this is what this is a definition of a derivation of Frobenius. Okay. Okay, so the proof of this is not too complicated. So let me just say what this is. Let me do this on another page because this is going to run out of space. Let me just take a picture of this. Okay, so delta 1 of, so let's recall what the rules are for these guys. Plus A to the P plus B to the P minus A plus B to the P divided by P. This is actually integral. This is an integral polynomial. By that I mean that x to the P plus y to the P minus x plus y to the P divided by P. So this thing's an element of z of xy. Okay, so if we expand this out by looking at the binomial coefficients. Okay, so this is one of the rules. The other rules, so here are the rules. The other rule is that is this messed up Leibniz rule. A to the P. Okay, so we have those two rules, and then and so you can see now that if you take delta 1 of A plus B minus delta 2 of A plus B, Okay, so what are you going to get? So this is, let's call this thing here junk. Okay, so this is going to be delta 1 of A plus delta 1 of B minus delta 2 of A plus delta 2 of B. Okay, and then this is plus junk minus junk. And those go away. So which is just going to give us, this is going to be delta 1 minus delta 2 of A. So this is just pointwise minus, let's see, what am I doing here? Oh yeah, that's right. Delta 1 minus delta 2 of B. Okay, so the derivation part, okay, so the derivation part of this, so this is the linearity. So we just do the exact same thing. Delta 1 minus delta 2 of AB. This is this. Okay, and now we break it up. And then B to the P. Delta 1 of B minus delta 1 of A, delta 2, B to the P. So we do the exact same thing with 2's everywhere. 2 of A, delta 2 of B. Okay, and this becomes, so now what do we get? So this becomes here. So delta 1 of A minus delta 2 of A, B to the P plus, and then here, A to the P, delta 1 of B minus delta 2 of B plus P. So then we have this stuff here times stuff. Okay, so, okay. And so if we work mod P, so if we define this to be D of AB, this is going to be D of A, B to the P, plus A to the P, D of B. So the last fact, okay, so that shows the lemma. So that completes the lemma. Another fact is that the p-derivations from one to another are a Torsor under f derivations from a0 to b0. Okay, so so this means that there's an action here which is full and faithful. Okay, so there's an action of here on here. Okay, so we need to show the action. Okay, so let's take a derivation. A0, B0, let's call it theta. Okay, and then let's take a derivation, A1 to B1, let's call this delta. Okay, then I claim, the claim is that theta plus delta is an element of the p-derivations from A1 to B1. Okay, so this is the action here. So this is, I don't know, that is a claim. This is what we claim. Okay, so let me show you how to do this. So this is just another direct computation. Okay, so here, so this is just going to be theta of A plus theta of B plus, and then we have delta of A plus delta of B plus that extra stuff, or what did I call it? Junk. Junk that depends on A and B. Okay, so here, now we just clump this. We can see that this is theta plus delta of A plus theta plus delta of B plus the junk that depends on A and B. And similarly, we do it for this one, AB. Okay, so this is the same thing. So we have theta of AB. So we have this Leibniz rule plus so here we have delta of AB. So maybe I need to do P times this here. But we'll see. Okay, so we have theta of A, B to the P plus A to the P theta of B plus delta of A, B to the P plus A to the P delta of B plus P delta A delta B. Okay, and this is, now we have to clump things. So now what do we do? So here, okay, so yeah, I think we will have to add a P. So here and here, Okay, so let's clump this together. So this is delta of A plus theta of B, B to the P, A. So here and here. Okay, plus, and then we have A to the P, then we have this term and this term. So this is equal to A to the P delta of B plus theta of B plus P, and then we have delta A, delta B. Okay, so here, let's call this delta prime, or I don't know, yeah, well, delta prime of A, B to the P, plus A to the P delta prime of B, plus, and now we're missing, so let's introduce them, theta of A. Okay, we have this, and what do we subtract? Minus. So we have this term and this term didn't exist. So all the terms except for, so we have theta A. Okay, so I stopped the video because I was confused for a second, but this is what's going on. Here, okay, let me go back here. This we don't need. Let's forget about this. Here we forget about this. The trick is, okay, is that this is mod P. So we're working modulo P. So here, this goes away. Okay, and now this becomes delta prime of A, B to the P, plus A to the P, delta prime of B. Okay. So that's the correct version. Okay. So the Torsor part, okay, shows that this is injective. So the action is injective. Is faithful, let's say. Faithful. It says that if delta plus theta 1 is equal to delta plus theta 2, this implies that theta 1 is equal to theta 2. This is obvious. And then the other one that says that for all delta 1, let's say delta 1 and delta 2, there exists some theta 1, 2, such that delta 1 minus delta 2 is equal to theta 1, 2. And this is clear. Okay, this is also clear from the construction, because we took the difference, and we defined it as a difference instead of an action. Okay, so that shows this. That shows it's a Torsor. Thanks for watching. Maybe I'll write this up a little bit neater.